Hey guys, today we're gonna go back. Well, not we're really going forward, but we're gonna go back a little and look at ionic radius. Now, ions we know represents charged atom. It could be positively charged, it could be negatively charged. We've seen positively charged ion by taking away electrons. And we sort of looked at the energy involved, how much energy is required to remove these electrons in ionization energy. We also looked at adding electrons to an atom, to turn them into an ion, negatively charged ion. And we also see the fact that if this atom is stable after receiving electron, a vast amount of energy should be released in electron affinity. So, when you take away electron or when you add electron, how will that affect the radius of the atom? And we know the word radius represents, the size of the atom. I mean, will the size increase by removing electrons, or the size will decrease when you remove electron? And what are the reasons behind, the difference in size according to radius of an atom? Well, we're going to do a couple of things. We're going to compare a couple of things. First, we want to compare the difference between an atom and its respective ion in terms of size. Then we're going to look at how the size of ion changes according from one element to another. So let's take a look at the first one. Number one, atom versus ions. Which one is bigger, smaller, whatever? So let's take a look at scenario A. And let's do an example like sodium versus sodium plus. Now you may be asking, why sodium plus? Is it possible to be sodium minus? The answer is, it is possible to have sodium minus. I mean, sodium can gain one electron, but it rarely does. So the ions that we're going to be looking at are what we know as the popular choice of ion. Now, we know how to determine that. Let's use Bohr as an example. Bohr does a great job in this. So in terms of sodium, sodium has 11 protons. Let's not worry about the neutrons. And sodium will have 2 electrons on its first shell, 8 electrons on its second shell, and of course, to compensate for 11 protons, it should have 11 electrons, like this. Now, if you were to ask somebody a question, or this is something that you already know you're supposed to do, what do you think sodium is experiencing right now? Well, the answer is this sodium right now is extremely unstable. It's not happy. The question is, how do you make him happy? How does he stabilize himself? Well, the best way to stabilize himself is to get rid of this electron. Because by getting rid of this, I now look like neon, a noble gas configuration. Because that's exactly what all atoms want to do, is to look like a noble gas, and it will try to look like its nearest noble gas. In this case, it would be neon, would it? By getting rid of this, getting rid of just one electron. So you can say that sodium ion, which is this, sodium losing one electron, is isoelectric with neon. Let's draw sodium ion then. Sodium ion would look like this. Now the question is, do I need to draw the empty third shell? And the answer is no, you don't have to. It's not going to make a difference because atomic radius or ionic radius is based on, the center of nucleus to the outermost shell, where there's electrons occupying them during ground state. So in this case, this is good enough. Now, which one is bigger? Okay, Na or Na plus. Now, this is going to be a very easy one, is it? Okay, your answer will for sure be Na. Why? Well, there's a couple of reasons. Extra energy level. Okay, that's no bigger reason than that. And the other reason, of course, is the amount of proton attracting the amount of electron. Here you have 11 proton attracting 11 electron. Here you have the same amount of protons but attracting less amount of electron. Right? 11 proton, only 10 electron. Because of that, a positive ion is always smaller than its counterpart atom. The second reason, of course, in this case, is because since the atom is smaller, there is less electron repulsion in cations. Okay, there are just less electrons to repel each other, causing the atom to be bigger. There's less of that, so therefore it's smaller. All right. Hopefully, this is not something that difficult to understand, but that's exactly how the scenario of atom versus ion would take place. So let's take a look at a different scenario here. Let's clear this up and let's take a look at scenario B. Okay, in this case, let's have fluorine versus fluorine ion. Now notice that I did not write F plus. F plus is pretty much impossible. Okay, if you look at fluorine, you'll know exactly why F minus is the way to go. So let's take a look at fluorine. So fluorine has 9 protons, and respectively it should have 9 electrons. Okay, 2 on the first shell and 7 on the second shell. There you go. Now the question is, how do you make fluorine happy? Fluorine is definitely not happy right now. It's pretty desperate, in fact. Desperate for what? Well, desperate for electrons, because if you were to add one more electron right there, fluorine will look like neon. It's Noah's noble gas. So that's exactly what he's going to do. Fluorine ion is isoelectric with neon. So what will fluorine ion look like? Well, it will look like this. Okay, an extra electron. Now, will an extra electron play a huge role in terms of its size? So the question is again, which one is bigger? Okay, now I can tell you right now that the answer is this one. This is going to be bigger. Now, is there an extra shell like we saw last time? No, there's no extra shells. So this idea is solely based on more electron repulsion. Okay, the idea here is that there's 9 protons here attracting 9 electrons. Here, same amount of protons, but extra electron to attract. Because of that extra electron, this is causing more electron repulsion. Okay, so in this case, because there's more electron repulsion, anions are bigger than, I guess, its respective atom. Okay, anions are bigger than atoms. Anyway, hope that is not something hard to understand or anything. I mean, it makes perfect sense, right? You know, when we looked at the cation, it had an extra shell. Of course, that's going to be bigger. But when you looked at, you know, anion has more electron than neutral, so therefore there's more electron repulsion. So, again, something to really to keep in mind. All right, now that we kind of explain how atom versus ion would work, so let's take a look at the second trend here. Number 2. Okay, let's have, of course, ions versus ions. Now, when we are doing ions versus ions, what we're basing, of course, is that we're basing on the most stable configuration. So if you're going to be gaining, or if you're going to be gaining electron, you're going to gain until you're happy. You're going to gain until you look like a noble gas. Because let's say, for example, oxygen gaining 1 is not going to make it's not going to make them happy. It's not going to be stable. Because oxygen at least want to gain 2. So we're going to see how the trend goes when oxygen gain 2 versus fluorine, which we saw only gains 1. Okay, so let's look at scenario A. Okay, let's look at the metals. Okay, let's look at the metals. Let's look at these 3 metal. Let's look at these 3. Okay, look at these 3. If I were to make ions out of these 3, what would the trend be? Would it increase going across, or would it decrease going across? We know from atomic radius, this actually decreases. We know that, okay? Because the number of shells stays the same, and there's just more protons moving along here, so therefore a stronger attractive force towards electrons on its valence shell. We know that, okay? From atomic radius standpoint, this decreases going along. But will it do the same when you're looking at ions? Well, let's check. Let's do this. So let's take a look at sodium plus versus magnesium, which is 2 plus, because magnesium want to lose 2 electrons, and I'll show you why very soon, versus aluminum losing 3 electrons, so 3 plus. So which one is biggest? Which one is smallest? Okay, sodium first. Sodium will have 11 protons. Okay, so here's sodium with 11 electrons. All right, but we all know that sodium is not happy right now. This is not sodium ion, this is just sodium atom. What does sodium want to do to become a sodium ion? Oh, yeah, that's right. Get rid of this guy, right? So let's get rid of that guy. There you go. Now he's an ion. Now, this is what we do with ion, though. You know, we need to do the right thing. Usually when we abbreviate ion, we give it a square bracket with its charge on the upper right corner. Okay? Okay, let's do magnesium. Magnesium have 12 protons, 2 electrons on the first shell, 8 electrons on the second shell, and 2 electrons on the third shell to make up 12 electrons. Hey, how are you going to make magnesium happy? Because right now he's pretty angry. I'll get rid of both of these electrons, of course. So that way he looks like neon. Now let's do that. There you go. Now he's an ion. Since he lost 2 electrons to become this ion, it makes sense that he's a 2 plus. Okay. Now notice that I did not write 1 plus here. It's really not necessary. Okay, aluminum. This is 13 protons, 2 electrons on the first shell, 8 electrons on the second shell, and 3 electrons on the third shell. Hey, how do you make aluminum happy? Of course, get rid of these 3, right? That's the easiest way to make him look like the nearest noble gas. So, hey, let's get rid of them. There you go. This is going to be 3 plus because we got rid of 3 electrons. Now the question stands. Okay, which one is the biggest and which one is the smallest? Okay. Well, it's pretty easy to determine if you think about it. These all have different amount of protons. Obviously, this one have the strongest amount of nuclear charge because there's 13 pluses here versus 11 pluses here. Take a look at the negatives. Notice that they're all the same. They're all 10 electrons, 10 electrons, and 10 electrons. So you have 11 protons here attracting 10 electrons, 12 proton here attracting 10 electrons, and 13 protons here attracting 10 electrons. So obviously, this being the strongest nuclear charge with really less, or the same amount, but less electrons to worry about, okay, this is going to be the smallest because this is the strongest, okay? At the same time, in comparison, they all have the same amount of electron, they all have the same amount of shells. This is going to be the smallest, okay? Less electron-electron repulsion. Well, really, electron-electron repulsion is the same between the 3. It is, because they're all 3 electrons, but then, of course, this having a stronger nucleus will, of course, attract these guys a whole lot more inwards. So, smallest will be this dude right here. Which means, if you think about it, the biggest will be this dude right here. Okay? So, according to metal decreases in size as you move along. Hey, kind of like atomic radius, right? So for atomic radius, as you move along, it also decreases. Yay! Well, let's take a look at scenario B. This time we're looking at the nonmetals. We're going to look at these guys. Okay? Would it continue to decrease and decrease and decrease? I don't know. Let's find out. Okay? So let's do P versus S versus Cl. And let's put them into their ions. Oh, argon doesn't make ions. Why did I circle argon? That's ridiculous. All right, let's take a look at what kind of ions phosphorus is going to make, okay? So phosphorus has 15 protons. So obviously it will have 15 electrons. So let's look at their electron count. 2 on the first shell, 8 on the second shell. There we go. 15 electrons right there. Now, how do you make phosphorus happy? Is phosphorus happy right now? Obviously, he's not happy. Okay? To look like phosphorus nearest noble gas, well, phosphorus nearest noble gas will be argon. To make him look like argon, I need to add electrons. So I'm going to add electron. I'm going to add how many electrons? I'm going to add 3 electrons. Okay? Now he looks like his nearest noble gas, argon. So by adding 3 electrons, you're adding 3 negative charges. So it only makes sense, of course, this has a charge of -3. Okay? So phosphorus is 3 minus. Sulfur. Sulfur has 16 protons. So I need 16 electrons. There you go. There's 16 electrons right here. To make sulfur happy, hey, I need 2 more. Okay, that way now I'm an ion with a 2 negative charge. Chlorine. Okay, chlorine have 17 protons. Well, I guess I'm going to need 17 electrons. There it is. Okay, so how do I make chlorine happy? Very simple. I just need 1 more electron because I'm just that desperate. This will be chlorine minus. So I turn all 3 of these atoms into ions. So let's take a look at which one do you think is the biggest and which one again is the smallest. Okay. Now, again, the difference between all 3 of these is the number of protons. Okay, the number of protons increases as we move along. So the charge, the nuclear charge is increasing, getting stronger and stronger and stronger. Now, let's take a look at the number of electrons. Number of electrons stays the same. They're all 18 electrons. They're all 18 electrons. So if you think about it, let's take a look at phosphorus. You have 15 pluses attracting 18 minuses. Man, that's a whole lot of excess of minuses. There's going to be a whole lot of electron repulsion happening in here. And not enough proton to really attract them. So if you look at the 3 excess electrons, they're going to repel each other a whole lot more than 2 excess versus 1 excess. Now, if there's more electron repulsion happening here, obviously the atom, this ion, is going to be big. Okay? Less nuclear charge, same amount of electron, therefore more electron repulsion. So it's not surprising that the biggest winner goes to phosphorus. Now, the smallest is pretty obvious. You have 17 protons here attracting 18 electrons. So that's 1 excess. So the amount of electron repulsion will obviously be the least. Check this out. So in this case, okay, in this case, what can you say about the ionic trends? Okay, so it looks like in terms of the trends here, this is the biggest, this is the smallest. So going across the periodic table, again, you're decreasing. Okay, so let's write that down. Oh, I'm glad you guys are hearing this bell. So this is decreases. But one thing you need to know is this, though. It's not a gradual decrease here. It's not a gradual decrease. From here to here, you actually have, from here to here, you have this little, not a little, but a big increase. Some people ask, what about silicon? What about the group 14? Well, the problem with the group 14 is that depending on its property, being metallic or non-metallic, it can gain or it can lose. So there's a lot of ambiguity. It's very ambiguous here. Okay. So, hey, that's pretty much ionic radius as a whole. So in terms of the trends for ions, you have, of course, decrease, decrease, decrease. Of course, then it will increase. and then decrease and decrease and decrease again. Okay. Anyway, guess that's it for today. Okay. This is Ionic Radius, and I actually have a lot of questions from the course pack that I want you to do. So we'll be doing that tomorrow. If there's any questions, hey, don't be afraid to ask me. Bye, guys.